Hello guys, let's prove that sin²θ plus cos²θ equals to 1 using complex numbers, and I'm going to be doing the proof in both polar form as well as in Euler form. Now first I'm going to start with the Euler form over here. Now in the Euler form we need to find out what sin² and cos² is. Well, let's look at the Euler form. So we have e to the power I² equals to cos² plus I sin². Now what can we do with this? Well, we cannot really do anything with this, because if you want cos², you can move that to the left, but then we'll have sin². We don't want that. We just want in some terms of e to the power I². So let's take e to the power minus I², because this is the same as e to the power I into minus theta. And wherever there is theta, put negative theta. So we'll have cos negative theta. But we know that cos is an even function, and f of x being f of minus x, simply cos minus theta is just cos theta. But what about for sine? Well, it's in fact an odd function. It's an odd function. That means that f of minus x is equals to minus f of x. Simply putting it, sine minus theta is equals to minus sine theta. So this minus goes over here. And we can see we have a something plus something, something minus something. We can do something with that. So let's try for cos² first. If we just add these terms, what I'll have is e to the power I² plus e to the power minus I² is equals to, here these two terms cancel each other, we have 2 cos². Meaning that cos² is just e to the power I² plus e to the power minus I² by 2. Now for the sine, instead of doing instead of plus, we can do minus, such that we have minus over here, and cos cancels, and we have I sin theta minus I sin theta, which is just 2I sin theta. And we can just move this 2I over here, e to the power I theta minus e to the power minus I theta by 2I. And here, let's just do sin² plus cos² and see what we have. Right here, when we square this, we'll have a minus b whole square, which is just ei theta whole square. But due to the indices law, we can just multiply with the power over here. So it becomes e to the power 2I theta. So basically, e to the power m raised to the power n is just e to the power m into n. And I'll just put the 2 at the front to make it easier. And minus 2 into a into b, and since these two are multiple inverses, that means when they are multiplied with each other they give 1, because this is just 1 by e to the power I theta, and multiplied with e to the power I theta gives 1. So this is just minus 2 plus the same thing with this, e to the power minus 2 I theta, and on the bottom we'll have 2I whole square, which is 4I square, and here this is plus. And I should write this over here. sin² plus cos² is equals to this. Now for cos², it's very similar, but instead of minus 2, we'll just have plus 2. And the rest is the same. And on the bottom, we'll have 4. Now what is I square? Well, from the definition of I, we know that I square is just negative 4. And this negative 4, since in the denominator, we can put the negative at the front, so it's in fact just this. And as you can see, we have 4 on both of these terms, so we can take that common. And on the above, we'll have this whole term minus this whole term. So simply e to the power 2I theta plus 2 plus e to the power minus 2I theta minus, this will be minus e to the power minus 2I theta minus plus 2 minus e to the power minus 2I theta. And as you can see, these two terms cancel each other, so does these two, and what we'll have is 2 plus 2, which is 4 obviously, and 4 by 4 is 1. So there is our proof for in the Euler form, sin²θ plus cos² is equals to 1. Now let's move on to the polar form. Now for the polar form, we have to first find a Cartesian form of some imaginary number. let's say it's in the form of x plus iy. So over here, let's say this is at a point like this. So that means this distance is x and this distance is y. So its coordinates are x comma y, but since it's the imaginary plane, it's x comma iy. So here, this is in the Cartesian form. To make it into the polar form, what we'll have to do is take this pole right here. Now let's say the radius of this pole or the distance is simply r. And here let's just complete this triangle like this. And as you can see, we can use the Pythagorean theorem to find that r is the square root of x squared plus y squared. Now, we not only need the length, but we also need the angle over here called the argument of the pole. And this theta can be anything, it depends on what this x plus I theta is. So here, this theta, we can do something with it. Since we're trying to find sin square theta plus cos square theta, let's see what is it in terms of sin theta and cos theta. So sin theta, this is here the opposite by the hypotenuse or the perpendicular by the hypotenuse, whichever you feel comfortable with. This is y by r. And for cos theta, this is simply here the base by hypotenuse, which is x by h. Oh sorry, hypotenuse here is r. And now we can find sin square theta plus cos square theta. So this is y by r whole square plus x by r whole square. Now this is y square plus x square by r square. And here if you square r over here, you'll get on the bottom, just the root will be cancelled. You'll get this, which is just 1. Now, you may wonder, well, here for the point or the coordinate, this y, even though the length is y, we put iy. But why not for sin theta? Well, it's because we're just trying to find the distance. So that means it's a scalar form. We want it to be in terms of its magnitude, and simply we do not care if it is real or imaginary, we just want the distance. And that distance is just y. From here to here it's just y. It doesn't matter if it's multiplied by I or not. But for the coordinate form, we need to find the exact coordinate, the position, so it requires the real and the imaginary information. So this is it for the proof of sin square theta plus cos square theta equals to 1 using complex numbers, which is interesting. So if you guys learned something new, please like and subscribe. Thank you.